All right, folks, let's kick off the presentation. I guess I also mean most of you are here, but it's morning, so I guess fair enough, like 50 people. Today, I'm gonna talk about the new sync component in TiCDC. This is gonna be a deep dive, so I'm assuming you already have a basic understanding of TiCDC, so about the whole architecture and about a bunch of different components. But just hands up, this talk is based on TiCDC 6.5.1. So if you want to take a look at the code, make sure you check out the red bunch and the red tag. So before we start, let me introduce myself. I'm Rustin, of course, a pin capper, working on data replication team. I'm also a Kaggle contributor and a Rust maintainer. You can find me on GitHub, Twitter, and my personal website. Of course, you can reach out me on the Facebook. Yeah. All right, let's get started. So, in the past year, we've been refactoring the sync component in TiCDC. This refactoring divided into two phases. In the first phase, we introduced a new sync and a new conflict detector. In the second phase, we changed the sync from push mode to pull mode. But today I'm gonna talk about the first phase. I believe the second one needs a separate talk because we did a bunch of work in the phase two. I'd like to thank Qupeng, Zhang, and Yang Fei, and Liu Zixiong for their contribution to this refactoring, and thanks to you guys. All right, let me give you a rundown of what is gonna cover today. First, I'm gonna talk about the architecture of TiCDC. So then I'm gonna talk about the old and new sync module design. After that, I'm gonna talk about the table sync and MySQL sync in detail. Finally, we will talk about the outcomes of this refactoring because we spent about like a couple months on this project. And of course, we will have a Q&A session at the end. If you have any questions during the talk, feel free ask them in the chat box. I'll answer it after the whole presentation. About the architecture, let me break down the TiCDC architecture for you. So, TiCDC is a distributed cluster, and we refer to each instance as a capture. I mean, we refer to each like a node as a capture, the physical node from the TiCDC cluster. Each capture can have multiple rules to process the data. You can imagine this whole picture as a capture, as a single node of a TiCDC cluster. So we can see there are two types of rules. One is the owner. The other one is a processor. But keep in mind, this is just a logic concept, not a physical one. So we only have one physical node, but have different logical parts. In a TiCDC cluster, you can only have one owner, but you can have multiple processors. The owner is responsible for scheduling tables and execute DDL operation. DDL is a quite special operation in TiCDC because we can't execute it multiple times. And we need to make sure it's only execute once. So that's why we I want to choose the owner to handle it, because TiCDC cluster only has one owner. The processor is responsible for replicating data for change fade, and each change fade can only handle one change fade at a time. So here we have one processor, and we have a change fade one, which has two tables. So, but maybe you have a question: what exactly is a change fade? You can think it's just a task. Like a user can write a configuration file for a set of tables, we can think it of as like a chain feed, tell the TiCDC which tables to replicate and how to replicate them. Write it to broker, the Kafka broker, or write it to MySQL server. So as you can see, the core component of the processor is a table pipeline. Here we have a puller, sorter, and a table sync. And we also have a global sync manager here. So today we are gonna focus on the table pipeline part because we wanna talk about the sync module. Talk about the table pipeline. Each pipeline is responsible for replicating data for single table, and it has 4 components. First up, we have the puller. The puller is responsible for pulling data from TiKV. Like we use a gRPC connection and gets the data from TiKV. The next one is the sorter. The sorter is responsible for sorting the data based on QMETS. This is this ensures that the data is replicated in correct order. And then we will have the mounter. This it's responsible for decoding the data from the row KV format because we get the data from the TiKV. So we need to convert the data from a row KV format to a structured format. We convert the KV value to a Golang struct. Then we can handle it in the TiCDC. Finally, we have the sync. The sync is responsible for sending the data to the downstream or to the target system. So this is the basic structure of a table pipeline. Today, I'm gonna focus on this part. Let's check the old sync design. As I said before, the sync is responsible for sending the data to the downstream or the target system. In the older design, we have different types of syncs. The first one is a table sync. The table sync, and you can think it more like a buffer to organize the data in table level. We need to keep it in order, and it's not responsible for sending data to the target system because it's not directly sending data to the MySQL server or Kafka broker. So, but we will use a sync manager and send the data to the target system. So, and the second one is buffer sync. The buffer sync is responsible for buffering the data in memory in the sync manager. You can think of it as a cache. The last one is MySQL sync. The MySQL sync is responsible for sending data to MySQL server, but it can be either MQ sync, the Kafka sync, or black hole sync. We use the black hole sync to test some stuff. You may already notice that the table sync and the buffer sync are quite similar in their function of buffering data in memory. Because here we buffer the data of one table here. At the same time, we also buffer the data here. So why did we have 2 separate syncs? I don't know. To be honest, I don't know. I'm not sure. So that's why we decided to remove the buffer sync in the new design because it's quite useless. Now you can focus on this part, focus on sync manager. The sync manager responsible for managing the table syncs. However, as you can see here is a circle dependency between the table sync and the sync manager. The sync manager creates and destroys and manages a bunch of table syncs, but table syncs still need to use a sync manager and write the data to the target system because it does not have the ability to access the MySQL server. It has to use the MySQL sync from the sync manager. So it's a pretty weird. We have a circle dependency here. But to make things worse, the sync manager also combines the buffer sync and the MySQL sync together. So in the sync manager, we have three different types of things in one place, in one structure. This makes code very complicated and hard to maintain. Because when you wanna check out some code of sync manager, you find that there are three different things in the same single file. So it's pretty weird. We have this kind of situation. Now let's take a closer look at the MySQL sync. When we zoom in the MySQL sync, we can see it's a combination of DML sync and a DDL sync. However, every time when we want to use a MySQL sync, we actually only use a part of it. Because, for example, for the owner, for the owner module, we only send the DDL to MySQL server. So we only use the DDL part. But for the processor, we need to send a bunch of row changes to the downstream. So we need to only use the DML part. But every time we want to use it or change it, you need to care about both DDL part and the DML part. This makes the code very hard to maintain, but at the same time, it's not make sense, right? Because we don't use those code in the DDL part, but we just combine them and into the one file. And every time you want to do some code change, you need to care about both of them. Let's take a look at the sync interface. As you can see, all things must implement this specific interface, which is quite complex. Because I already ignore some function from this interface, but still we need to care those functions. But in those functions, some of which are thread safe, and while others are not. Additionally, some methods are blocking, but some others are not. So here you can see the image routine events is blocking, and the try image routine events are non-blocking. So it's a little bit weird. We have a different implementations and different blocking or non-blocking methods here. This actually makes it very hard to implement new sync, especially we combine the buffer sync and the MySQL sync in the sync manager, and combine the DML part and the DDL part into the same interface. It makes no sense. It's a little bit crazy, and it's really tough to maintain those code, because if you don't have a Golang, I mean the IDE from the JetBrains company, when you wanna read some code, it's really a big challenge, because every time you wanna check out the call stack, and you find it's all the same function from the same interface. It's just a chaos. You don't really can understand the whole call stack or the whole code chain of those code. So it's pretty easy to get lost in the code. Let's take a look of data sequence. Maybe this will help you understand how the code works. The process starts with the sync node. Whenever the sync node receive a row change event from the TiCDC, it adds it to a buffer, to its own buffer. Once the buffer is full, it calls the table sync to emit the row change events. The table sync then adds the routine events to its own buffer, another buffer, right? And after that, it will wait for a flash signal. When we add the event to the buffer, we need to keep it in the memory and wait for a signal, when I can write the data to the downstream. Once the sync node receive a signal from the previous node, it's called the table sync to flash the routine events. Here I want to explain about the signal, or what kind of a signal can advance the whole process, or let the table sync to write the data to the downstream. It's more like a timestamp. We can get a timestamp from the TiCDC or from the previous node, or from the sorter. When we get a specific timestamp, it will tell us before this timestamp, I already sent all the data to you. Right now you can flash those data to the downstream because there is no any data after this timestamp. So we use this kind of a timestamp to flash our routines. Here we call the flash routine events function of a table sync. The table syncs then calls the sync manager to emit the routine events and flash the routine events. As you can see, all the functions are same because they implemented the same interface. So the call stack is pretty crazy. You call the same function at least 3 times. But the worst situation is that every time when you call those functions, it's just add the routine to its own buffer. Actually, the sync manager also has 2 buffers. One is for routine events, and the other one is for resolve TS. Once the buffer for the routine events is full, from the buffer sync, the sync manager will cause the MySQL sync to emit the routine event. Again, the same function, but from the different implementation. Finally, the MySQL sync converts the routine events to the SQL and then sends them to the MySQL server and execute it. As you can see, this process is quite complex, and there are several buffers involved. The first one is from the sync node, and the second one from the table sync. And the sync manager even has the 2 buffers here. And if we use the Kafka sync here or MQ sync here, probably we got another buffer, because for the Kafka producer, it also has a buffer. So in the whole process, probably have at least 4 buffers or even 5 buffers involved. Overall, the process requires a lot of coordination and careful management of buffers to ensure the data processed correctly and efficiently. So it's crazy, when you want to check out those code, you find that every time it's just called the same function. And it's just do the same stuff, but it's all from the same interface. It's pretty challenging when you want to read those code. So let's summarize the issue with the old thing. There are several problems that need to be addressed. First, there is a circular dependency between the sync manager and the table sync, which makes it difficult to understand and maintain the code. Secondly, there are too many buffers. As you can see, we at least have 5 or 4 buffers in the whole process. So it's really hard to manage those buffers and can lead to some memory issues. For example, out of memory, because we copy the same stuff at least 4 times. Thirdly, the sync leaks table information everywhere. For example, from the MySQL sync perspective, I don't care the table info, because I just more like a writer or more like a DB connection. I don't care about the table information. I only care about what kind of event you like push to me. I'll convert it to SQL and execute it. It's not about the table. It's just about the routine. So right now we dict the table information everywhere, like from the buffer sync, from the table sync, from the event sync, from the sync manager. It's all about the table, but we don't actually need to like design it in this way. Fourthly, the core stack is too deep, and it's make it it's making the whole code hard to debug. Because every time you want to find the implementation of this function, you will find a bunch of different implementation, but the name is the same one. Fifthly, the abstraction is very complicated, and there are too many functions in the single interface, which makes it hard to add new things, because every time you want to implement a thing, it's just a bunch of functions you need to take care. But maybe you only care about the some of them, not all of them. So it's pretty bad experience if you want to add a new things. And finally, some implementations are not thread safe, but some implementations are thread safe. So usually we want to keep them all thread safe, because every time you want to change something, you need to make sure the change is thread safety. It's pretty hard if you don't unify the whole implementations. So talk after the old thing, we can take a look of the new things, how we solve those problems. As you can see, this architecture is much simpler than the old design. Basically, we got rid of sync manager here, and also we got rid of the buffer sync. Now we only have two types of syncs: table syncs and event sync. The table sync is just a simple buffer that stores the routine events. On the other hand, the event sync is responsible for writing those routine events to the TiCDC system. We made the table sync more focused on by limiting its scope to be just a buffer, and it does not have any knowledge about the TiCDC system, about the MySQL stuff. It's a pure a buffer for a specific table. And as for the event sync, we don't have any table information here. We just have some workers that handle writing the routine events to the TiCDC system. We don't care about the table information here. Every time you give me an event, I write the event. It's we don't care about the table information. We just care about what kind of event you wanna it's write to the downstream. So let's check out the interface to see how we implement this design. First, the table sync uses the event sync to write routine events to the TiCDC system. So only one direction. Second, the event sync is an interface that has multiple implementations. We have a MQ event sync. I mean a message queue event sync, for example, Kafka. The translation event sync, you can write the data to TiDB or MySQL. At the same time, we got a new thing called a cloud storage event sync. You can write the data to the S3 or other a cloud storage service. At the same time, we separate the DDL sync and the event sync. I guess it's a pretty a good idea, because right now you don't need to care about the DML part if you wanna implement a DDL sync. For example, in Kafka, we use a async producer to write routine event to the Kafka server. So we need to care about the error handling and all the like async stuff. But we use a sync producer to write a DDL event to the Kafka because it's just a simple like a DDL operation. You can use a sync producer instead of a async producer. So right now you only care about the sync part here and the async part here. You don't need to combine all the code into the same file or into the same module. It's extremely simpler. After like this abstract, we can check out the code. As you can see, the table sync interface is super easy or super simple and easy to use. They are just like four methods you need to know. First up, it's we got the append row change events method. This one is used to store any row change in the table sync. The next one is the update resolve TS method. This method writes all of the cached row change event to the event sync. This part I already talked about it before. We use a specific timestamp like this resolve TS to tell the on the hood sync try to send the data to the downstream, because if you get this resolve TS, it means all the data before this resolve TS already in the memory, and there is no data after this resolve TS, so you can safely write the data to the downstream. And the third one is called get checkpoint TS. This one is used to get the current checkpoint TS of the table sync. The checkpoint TS means for this like a specific timestamp, we already written all the data to the downstream. We already got the execute result. It's already sent to the downstream successful. So we can return this specific like a timestamp to tell the user we already finished all the data before this. We already replicate the data before this specific checkpoint TS timestamp. So as you can see, the table sync is just a simple buffer. This will add the data to the buffer. This will flash the buffer to the like a downstream, and this will responsible for give the progress of this table sync, and that's caller or top level module knows what's the progress of this specific table. The implementation of the table sync is really easy to understand. Basically, we have a generic structure that can write any type of events. It's really just depending on the system. We may want to send the row changes to the Kafka. So usually we send it by message. I mean row by row. And if the downstream is like a relational database, we need to send it transaction by transaction. So here we use this E to represent like a event. It can be a row chain event. At the same time, it can be a transaction. To store the events, we use a buffer slash, and we use a max resolve TS as a signal to know when to write the events, the buffered events to the event sync, to the downstream. We also have a progress tracker here to keep track of the progress of this table. When you call the get checkpoint TS method, I mean, if you want to get the progress of this table, it's just calculates the progress from the progress tracker and return a specific like a timestamp to you to tell you I'm already replicated the data at least to here. So finally, we got the backend sync. As you can see, it's just a event sync. which just its interface pretty simple. Only have two functions. It's extremely simpler than before. You can notice the here is the ret events function, and its argument is a callbackable event. Because we want to make our whole ret process be asynchronous. So we use a callback mechanism to achieve it. Every time we couple a callback with a routine event, so we can know when the event already written to the TiCDC system. For example, after you send the SQL statement to the downstream and execute it successful, then we can call the callback to tell the progress tracker this event already written to the downstream. You can update some information from the progress tracker. To help you understand the table sync and the event sync better, let me show you the new data flow. The data flow also starts from the sync node. I divide the data flow into 4 parts. The first part is about the add event. When the sync node receive a row change event, it's called append row change events method of table sync. It's just a simple add the event to its buffer. And the second part is the update resolve TS part. I mean try to flash the data to the downstream. When the sync node receive the resolve TS, it calls the update resolve TS method of the table sync. Then the table sync calls the add event method of progress tracker. It retains the callback, and it also gives the event ID. At the same time, we add a resolve TS to the progress tracker. Then we can call the ret events from the transition event sync. I mean the MySQL sync. With the callback, because when you want to add the event, the progress tracker give you a callback, which contains some information about the progress. So here we send the event with the callback to the transition event sync. And in the transition event sync, we just simply add it to the conflicts detector. I'll talk about this part later. It's more like it's more like one module for detect the conflicts between different transitions. And the third part is the async ret events part. When the conflict detection is done, the MySQL sync will execute the SQL statement and handle its SQL result. Then it's called the callback method of the progress from the progress tracker to notify the progress tracker this specific event is written to the TiCDC system. You can update some information about this specific event. So the last part is the get checkpoint TS part. When the sync node calls the get checkpoint TS method of table sync, it's just called the advanced method of progress tracker to calculate the current process for this table. So it's just calculate a specific time stamp to tell the scheduler or other top module we already read this table or replicating this table to this specific timestamp. Basically, in the system, there are only one buffer this time in the table sync. The event sync is a pure a writer or a bunch of workers to send the data to the TiCDC system. We make sure not leak any information to the event sync because it's called the event sync. So it's only care about the event. For the transition event, it's just a transition event. For the other Kafka sync, it's just a simple row change event. After we understand the data flow, we need to figure out how to track the progress of the table sync. because we write it asynchronously. Because here probably we got a bunch of MySQL workers, so we also write the data concurrently. We need to make sure we can calculate the write process of this like a table. So we introduced a new structure called a progress tracker. Let's see, we have we received some events, for example, translation 1, translation 2, and the result TS2, and other like translations and result TSs. Those events already sorted by sorter. Now the question is, how can we track the progress? And since we write those events concurrently, we need to make sure update the progress at the right time. We can't update it too early or too late. Updating the process too early can cause some correctness issue. For instance, if we update the progress after TXN 3 -1 and TXN 3 -2, if we already read those events to the TiCDC system, the checkpoint TS we can update to the result TS3. However, if the translation 1 and the translation 2 are not yet written to the TiCDC system, the checkpoint TS actually should be result TS2. It cannot be like a result TS3. So if right now you just update to the result TS3, if the system crashed at this specific point, we will lost the translation 1 and translation 2 because it's still in memory. On the other hand, updating the process too late can cause some latency issues. So we need to update the progress as soon as possible to reduce the latency. Because from the user perspective, we want to make sure the upstream and the downstream have the minimum difference. So we need to keep we need to update the progress as soon as possible. So here, the naive solution is just to use the current order to track the progress. We can simply use a list to store the event sync with the associated event ID. As I said before, every time you want to add something to the progress tracker, it will give you an event ID. For the normal events, here the key is the event ID and the value is nil, because we don't care about the content of this event, because we only care about does this event already written to the downstream. But for the result TS, the key is the event number, like an event ID, and the value should be result TS, because we need to use this specific timestamp to tell the caller or tell the top level module about the progress of this table sync. So every time when we write an event to the TiCDC system, we can remove the event from this linked map. When we want to get the checkpoint TS or get the progress, we can iterate the whole linked map to find the first normal event. Then we can update the progress to the last result TS before this normal event. For example, here we got those events, 5 events. If we already written the event 1 to the downstream, we can simply remove this event from the linked map. And when you want to get the progress of this table, we can just iterate from the first element and try to find the first non-nil event. I mean, the value is non-nil. So the first one is the event 3, because we already removed this one. So then you can update the progress to the result TS1, because before this specific timestamp, we don't have any other data, so we can safely update our current progress to this specific point. It works, right? It's also pretty simple, but it's not good enough after we test it in our real environment. Since we have when it comes to the performance part, using a map to store the events is not quite efficient. Since we have multiple workers write events to the TiCDC system, using a map would require getting a log every time when you want to write an event, when you want to update something. So it's actually pretty bad from the performance perspective. To improve the performance, we can use a list. We can still use a list to store the events because we already sort it in the sorter. We don't want to introduce other stuff in this module, so we can keep this order. But instead of use a red lock to protect the entire list or entire map, we can narrow down the lock scope. So we can use a bitmap to indicate the progress and use a atomic operation to update it. It's extremely faster because every time you only just need an atomic operation instead of get a whole big lock. So we can use a integer to store the bitmap, where each bit represents an event ID. It represents event. So for example, if the event ID is 3, so the bit index is actually also 3. We use the 3 mod the 36, so we got 3. This one. And after writing an event to the TiCDC system, we can use the atomic operation here to set the corresponding bit to 1. If we write the event 3, then we can update this bit to 1. When you want to get the checkpoint, yes, it's pretty similar. You can find the first 0 bit to tell the top level module the progress, because if it's still 0, it means there are still a bunch of events before this event 3 needs to send the TiCDC system. It's still in memory. You can't update the result TS to here because maybe those events already in the event sync, but still in the memory. So this is a big improvement. But as you can see, this makes code more complicated. But I guess it's fair enough, because every time you wanna solve some performance issues, it's always getting complicated. So that's all about the new table sync, about its data sequence and about its progress tracker. Those 2 main parts already finished. And actually, in the previous section, we check out this diagram. You may notice the MySQL sync actually involved conflict detection progress. Now let's see why we need this conflict detection. For example, let's see, we received a massive amount of events, maybe thousands, 10,000 events. We can't afford it to send them one by one. It's it's ridiculous, right? You can't write them one by one. So we need to write them to the TiCDC system as quickly as possible. To speed up, we can have multiple workers here, maybe 16 or 32 workers here. Those workers can write the events to the TiCDC system concurrently. However, we must ensure that events are written in correct order, because maybe one transition is a conflict with the other transition because they modify the same rule or the same like a primary key or same unique key. So we need to introduce a detector to identify the conflicts. We only allow the non-conflicting events to written concurrently. It's not because we need to make sure the correctness. For the events, like that's already like a conflict, we must wait until the previous event has been written to the TiCDC system. Then we can write the like a conflict like events. Let me give you a like a example of a conflict. So here, if we receive those events at the same time, we would have a conflict. For example, DML1 and the DML4 conflict because they both modify the same the same primary key. Similar, the DML2 and the DML3 conflict because they both modify the same key. At the same time, the DML5 conflicts with all other events except the last one because it's also like a modify the primary key 1 and a unique key like a 3. So how do we detect the conflicts? Actually, in the older approach, we use a union set to store the events and identify like using the primary key and the unique key. If two events modify the same key, we can put them together as a group. So for example, if we ignore the DML5 for a moment, we can group the events as follow. Like a group 1 here, group 1 contains the DML1 and the DML4 because they modify the same primary key 1. And the group 3 contains only DML6. And a group 4, group 2 contains the DML2 and the DML 3 because they already modify the same primary key 2. So if we don't consider the DML5, we can just think those group as a different worker. We can send the this group for worker 2, this group for worker 1, and this group for worker 3. We can write those data concurrently, but if we consider the DML5, it's pretty bad because DML5 also conflicts with the group 2 and the group 1. So we must wait until the other events like a group 2 and a group 1 have been written to the TiCDC system before we can write this DML5. Actually, this is a significant problem. If we have a large number of events, we will have to wait for a long time before we can write the DML5. So this is terrible. We can actually, as you can see, we can write the DML6 at any time because it doesn't conflict with any other events. But from the older approach, it's like a DML5 will cause a stop word problem. It will stop the whole detection process before the previous events written to the downstream. So we need to find a solution and to solve this kind of a stop word problem. So we introduced a new conflict detection algorithm. We use a DAG. We use a DAG to store the events. First, let me just define a few terms. A node is a transition that has not been executed and received by the conflict detector. An edge like it is a relationship between two transitions. If you like a transition to modify the same key as a transition one, we can draw an edge from like a to like from the transition to transition one. At the same time, we do like a optimization. If there exists like a if there exists a path, for example, transition to the transition A, transition B, or to the transition Y, then we can ignore the edge between the T1 and the T2, because this is like a pretty complicated if we have this kind of like a edge, and also it will simplify our implementation. So here the same events, but this time because T3 modified the same key as a T2, so we can draw an edge from T3 to the T2. And similarly, like the DML4 modifies the same key with the DML1. So we draw like an edge from T4 to T1. And because T5 modifies the same key as a T4 and the T3, so here we can draw like an edge from here, T5 to T2 and the T5 to T3. But for the T6, it doesn't modify the same key as any other transitions. So there is no edge for this one. Right now, we can solve the stop word problem by using this graph. We can write the T6 to the target system at any time because it doesn't conflict with any other transitions. And this time, we still cannot write the T5 until the T4 and the T3 written to the downstream. So, but this time, we don't need to stop the whole word. We can write the T1, T2, and the T6 concurrently. Because this is like a single node, we can send a single node to the worker. So this will help us like solve the stop word like a problem. We don't need to send those two groups like an entire group to the worker. We only send the transition one by one, but we still keep the order to avoid the correctness issue. This is the biggest change in the new MySQL sync. I suggest you read the code and understand how it works. It's a little bit complicated, but if you understand the whole graph and understand the whole approach, it's like maybe you can understand the code. And yeah, I guess I'm already running out of time. I'm sorry. But let me just finish the last page. Yeah, thank you guys. All right, let's talk about the outcomes of this project. Firstly, we were able to improve the performance of MySQL sync by replacing the union set with the direction with a DAG. So this results in a significant improvement in the sync's performance. And we use a real customer workload to test it. We can achieve about 60% throughput improvement. So, but this is with the second phase with the pop-based sync refracting. So it's a big. This is a big improvement. Secondly, we have removed some buffers from the old sync and replaced them with only one buffer in the new table sync. This not only saves the memory, but also reduce some chaos. Thirdly, we improve the abstraction and the data flow by using only one data flow in the new sync. This time, we only replicate data from table sync to the transition event sync and to the MySQL server. It's pretty simple, only one direction. Firstly, we have improved the testability of sync by separating the DDL part and the DML part. We also have a better maintainability because all function in the event sync are thread safe, and when you want to change something, it's like easy to get the thread safety. And the last one is it's pretty easy to add a new sync because we in the old sync we mixed all the syncs together in the sync manager. This made it difficult to stand and add new syncs. But right now you only need to care about the event sync, and you don't need to care about the table sync because the table sync logical is quite common. We already implemented it. You can reuse it for other syncs. So this makes it easier to add new syncs. Yeah, that's all my presentation. I hope you enjoy it. If you have any question, I can answer those questions. Probably we don't have any questions here. So maybe we can, end up this. Do you have any question? Okay, cool. Thank you, guys.